So this is the final part of all the lectures, and there will be two more hands-on, and we're finished. So moving on from this HP FMM, just a brief description of. Oh, before I go to this, maybe I should review. So since I've talked a lot about FMM, I just thought it would be nice to show the history of FMM over the years. So these are all work that are related to the fast multiple method, and the different colors represent the papers from different areas of science, astrophysicists, molecular dynamicists, and computer scientists, applied mathematicians have all contributed to the advancement. And so the applied mathematicians, developed all the underlying math. The focus initially was on, the extension to from 2D to 3D, and then to more complicated equations, all that have Green's functions, though. So all of these equations, although the ones that came later are more challenging to solve, are all functions, the PDEs that have Green's functions. And so we can all now solve all of these equations using fast multiple method. But also, there's also a more generalized approach to FMM, where even if you don't have these equations, you can do a kernel-independent FMM or block box FMM. These can handle, or SVD-based FMM. These can handle other types of equations which are not these equations, like Laplace, Helmholtz, and Stokes. So you can do things like exponential functions or Matern functions, more complicated radial type functions that people use in statistics. And also, from about the year around here, 2010, a lot of papers on the HSS or H matrix, these papers started to come out. And now we have so many that I haven't written in this table here. From 2014 onwards, there's so many that I can't even fit into this page. So, and also another branch of computer scientists were looking at fast multiple methods from a completely different perspective. So, how to parallelize, not necessarily extend its capability to more general problems or anything, but things like how to load balance, how to partition, different ways of partitioning, use on GPUs, or other tools, using tools like Charm++, and in the field of optimizing the code, you also have these ways of not necessarily extending the capability of the code, but just making it faster by using different types of expansions, or different ways of determining the well-separatedness, and the variable p approach, and things like this. So there have been different contributions, and not all of these features are inside one code. So you have all of these studies, but we don't have a one big community code, like PETSI, that has all these features, for example. So maybe in the future we might have something like this, but at the moment we don't. So this is the brief history of what has been done in fast multiple methods. There's of course much more than this. There's 500 papers that I could cite that made significant contributions to the field of fast multiple methods, but I'm just citing here a very brief, a very fine selection of that. And then so I mentioned that there are so many studies on the matrix variance now. So I've just summarized like this is, you think of this as like a news update for these H matrix, HSS, and FMM related publications in 2015. So this is like, think of this as a news feed, and it's just highlighting some pictures of some of the work that has been done very, very recently. So I'm just trying to show you, a little bit of the new stuff, because everything that I've mentioned up to now is considered old stuff. I'm just, doing it because it's a lecture, and I, started to start from the basics. But now this is considered, the cutting edge of this research. So now I'm taking you, fast forwarding to the bleeding edge of the research that's done in this field. So this is and I think you can understand the essence of all this work because of the information that I gave you throughout this lecture. So now you're ready to sort of understand, the essence of what the contribution of these works are. So that's why I'm showing them to you here. So this one is one of the techniques that sort of have, I remember that I mentioned the weak admissibility, the ones that don't divide the box so much, have a problem when you go to higher dimensions. So this is a technique that tries to solve that problem, but still continue to use the weak admissibility. But it does it in like a sort of a dimension reduction fashion that even if you're dealing with a 3D problem, it sort of reduces that to a 2D and then a 1D. And it's sort of, there is an analogy of this work and the work on, like the hierarchical Schur complement that you're doing. So there's like, if you draw a picture of this, it's like, you have a volume and then a face and then edge and then, you're separating the separator kind of picture is done in this kind of dimension reduction. They call this a dimension reduction skeletonization. Yeah. So, this work here is yet another way to keep the weak admissibility, but then, so I told you if you do this for high dimensions, these off-diagonal blocks don't compress very well. So this block here becomes very large if it doesn't compress. But then what this does here is this one isn't that one. This one is just using the HSS for inside a multifrontal method. So the method I was about to tell you, actually, which one is it? It compresses the dense block here further by nesting the HSS. It's called HSS2D. But it's the same person that works on it. This is that kind of technique. Also, there have been combinations with, this is more like an implementation issue, but this has been done on MPI. And in terms, this one has been done on Xeon Phi, for example, the Intel coprocessor that's like it looks like a GPU from Intel. So this kind of work has been done on these new architectures. And I mentioned that the H matrix or HSS matrix consumes a lot of memory because it stores many things. But this one tries to tackle that issue by not creating all the dense things at once, but trying to do it line by line. And also you have on the FMM side, FMM calculates like a point operation between points. It doesn't do the continuum integration, but this one is for handling actual volume integrals. That means not discrete summation, the sigma, but actual the integral operation throughout the volume by using like a quadrature points to represent. Well, they turn into points eventually, but it has its own sort of discretization scheme built in, so it can handle continuum integrals and not the discrete point summations. And these approaches, this one is sort of a hierarchical approach that sort of does it bottom up. So usually you look at the problem from the top and then you think about how to subdivide the region further. But this one is, so it has advantages when you have jumping coefficients. So say that you're solving Poisson equation, variable coefficient Poisson equation, like for a reservoir or something, and then you have these jumps in the coefficients. So you can actually draw the line, of the separator that matches with that jump in the coefficient. And if you're doing it bottom up, you can, always align. If you're doing it top down, it's sort of difficult to align that with the, well, maybe you can do it, but it's more natural to do it bottom up. So this is that kind of technique for variable coefficients. And butterfly factorization is yet another idea for doing, so this is the hierarchy. Think of this as the target tree and this as the source tree. What it does is it flips the source tree and it does the operations against all levels. But so the highest level of the target tree is interacting with the lowest level of the, so this arrow here, lowest level of the source tree. And it does this kind of operation for all the levels. And then it looks like the butterfly communication in FFT. So people who have studied FFT know that there's this thing that has x's, that go from top to bottom and then half the distance and then, half of that. And it looks like a butterfly. So it's called the butterfly communication in FFT. But this one looks like a butterfly factorization. So it factorizes according, it has a log n, you do it log n times because there's log n levels in a tree. And so it's an n log n method to solve in this kind of form. And also inverse FMM is something I briefly mentioned earlier. So FMM can do the matrix vector multiplication, but you can actually do the inverse operation now. And since you can use it as a direct solver in that case, if you do it with lower accuracy, it becomes a good preconditioner. So this work introduces the inverse FMM and use it as a preconditioner. And they have nice pictures that, they sort of explain how you reduce the fill-in when you do this inversion operation. So this is a like brief news update of recent work. So now you know what's the state of the art in this field. So, yeah.
Can you say a few more words about the multifrontal plus the HSS plus ER5?
Okay.
So that sort of grouping of a tree.
Yeah.
Is that the multifrontal elimination tree, and they group some labels together?
Yeah. So I think that the idea is, it's the same as these. Well, so this is solving LDL and not LU or Cholesky, but so this one I think is doing like a standard LU or something, and then for the Schur complement, it's compressing with HSS. So it's the same idea. You do multifrontal, and then the dense Schur complement that it forms, you apply the HSS, and this is just simply doing that on Z on phi. So I mean, if you don't look at that, it's just the compression being applied to the Schur complement. So it's
So what different level of Schur complement they start?
Oh yes. So the highest level has the deepest tree, right? But you can see that the lower, the smaller Schur complements, you just make a shallow tree, and it doesn't create a very deep tree of hierarchy. But the off-diagonal blocks you can think of, if you can imagine, these pictures here. The off-diagonal blocks of this biggest Schur complement are, like this, and then it's refined to like a, deeper level for the big Schur complement. And at some point, it doesn't make any sense to do it hierarchically anymore, so you just do the dense linear algebra directly. So I don't know at which level they switch, but the key here, I think, is to use the Z on phi efficiently. You want to switch to the dense operations earlier, because Z on phi can handle the dense linear algebra, the dgem quite fast, but well, maybe it's not dgem. It's the dense inversion, or no, the solve operation, and you want to calculate. You want to switch to the completely dense and not hierarchical version early if you're using GPUs or Z on phis. So there's sort of a, nested hierarchy here because you have the hierarchy of the Schur complement. Well, you have the sparse hierarchical structure, and then inside the dense blocks, you have another sort of compressed hierarchical structure for the HSS matrix. Yes, and yeah, so when you read this paper, you just need to know where it switched to the dense, because I think that's the interesting point in the, going to the Xeon phi's. So
this can get with say compression in the, for example, root label by using HSS.
Yeah, I think you get fairly good. So like the paper I sent you on the low rank properties of the Schur complements, that probably explains something about how much this can be compressed. Okay, so I just not so critical, but this is something about my code that I'm developing. So what I want to do is I want to have separate modules for my FMM code. So I've developed many FMM codes, and every time I have to develop all these things, but I end up just copying from the old kernels this part, and usually I rewrite the tree structure, but like the MPI part, I'm developing separately and have other people working on it. So it's nice to have like a modular view of these different components. And so what a FMM code should look like in the future is, I think it should have like these P2M, M2M, M2L. These parts should be developed like well, first the equations should be developed by applied mathematicians, and highly optimized versions of the code can be developed by the coding ninjas. And the tree part is of interest to a lot of computer scientists, but they have no clue what's happening inside the kernels, and they're not interested in that in general. But every time they try to do some experiments, they depend on having these other components. So it's good to have like a modular view, and maybe even have like different codes that just do this and do this and then do this part, and then just download each of them and run them together. And that way, because each of these parts have people from different areas interested in working on them. So it would be nice to have the different parts being worked on by different people. Okay, this is my final slide. I just wanted to briefly mention about what happens to the matrix version when you do it in parallel or in distributed memory. So I explained to you many things about how to partition, and the concept of the local essential tree for the fast multiple method. And what happens when you want to do it for the matrix version? So first of all, the big difference is you in the fast multiple method, you don't actually store this matrix at all. So it's not a problem to have all you have are the two trees on both sides in the fast multiple method. So the analogy would be FMM has this tree here and this tree here, but the H matrix stores sort of the tensor product between these two trees. So it has this tree being multiplied in a dimension. In the other dimension, you have this tree. So the way we partition the FMM is such that each of the ranks, MPI ranks, have a subtree owned as the target, and then you collect the parts of the global tree from the source tree that this target tree needs. And that was called the local essential tree. So what does that look like in the matrix form? That looks like this. So each of the targets are the rows, and all the source tree spans the columns. And so the local essential tree is actually this block here, right? There's a direct correspondence. So this tree being white here and only having this big blue block is sort of similar to having only this big blue block here. You don't need these diagonal dense components from this column. You need just the big components from this column here. And so you just get this block here. And same for here. You just get the not so dense parts of the source tree. And then for yourself, my rank, you have the fully dense thing. So the parts that need to be communicated are this part, and this part you already have. So also this part. So the local essential tree is like this whole row of your H matrix. Now, when you do these operations, if you're just doing a matrix vector multiplication, even for the matrix form, you don't need to communicate any of the matrix because basically what you need to do is send all the basis functions that construct basically what the local essential tree is sending, the same information equivalent to the multiple. You just need to send those V bases. And then you construct what is necessary, the matrix entries, locally. So this part you only construct locally. And then all the operations that need to be done to obtain these, the matrix entries can be constructed locally from what you have sent for the bases. And so there's no need to communicate any matrix elements if you're just doing a matrix vector multiplication. So basically you can refactor the hierarchical matrix so that you don't have to send any of the matrix elements. Then the problem is, so say that you wanted to do matrix inversion, then you do need to start sending all the matrix entries. And this is more so if you factorized in the beginning, and then so the factorization part requires the sending of the matrices. Once you factorize, then if you just store this part locally, then the apply phase you can just keep applying without communication. But the factorization part is the part that sort of requires other information about the matrix elements from the others. So there is another way to invert a matrix that doesn't require you to send all the information. It's just you can do so if you iterate to obtain the matrix at k plus 1 through the Newton-Schultz iteration, then you can turn a matrix inversion into a matrix-matrix multiplication. And so this was suggested by different people at different times. So basically what you need if you want to do a matrix-matrix, so this was for a matrix vector. If you want to do a matrix-matrix multiplication of a hierarchical matrix, then so the target would be this whole thing here, because it's a matrix-matrix. So for a matrix vector, all you need is the vector here. So the part you need is the local essential tree. But for a matrix-matrix, the target is this light green part. And then the source is actually, maybe it's difficult to see, but there's a dark part that's not entirely black in this figure. Those are all the parts that you need to send. And so it turns out that you actually still need to send a large portion of the remaining matrix if you want to do the matrix-matrix. And so there's no, but it's more parallel in the sense that it has a shorter critical path during the matrix multiplication than having to invert it, because there's a dependency when you need to do the inversion. Matrix-matrix you can just do in parallel. So, but still, when you try to do more complicated operations using the matrix form, then it's not very scalable, and this is mentioned by many people. So we still haven't found a very scalable solution for more complicated operations for these hierarchical matrices. And the matrix vector we can do very efficiently, and the FMM does that very efficiently too. But I don't know how, for example, the inverse fast multiple method scales. There haven't been any studies on that, because every time you want to do something that's not a matrix vector, the communication becomes quite complicated for these methods. So this is sort of a remaining question, an open question. And so this is sort of the end of the lecture. It ends with like some questions that haven't been answered. But anyway, I just wanted to explain what happens to these matrix forms when you want to run them on a large machine. So this is like the end of my slides. So now, without taking a break, I'm just going to move to the coding session. So let's switch to the code and see what happens with the kernels. Or should I? Okay, now maybe I'll review what we did where we left off last time. So just to review, we finished the adaptive tree, step 8, and this is all online. So if you go online and download all the new code, the latest one is step 8. And then yesterday we did all the parallel stuff, but we didn't touch step 8. So for those of you that did the exercise of parallelizing, steps 5, 6, and 7, and 8, you might have a parallel step 8. But let's look at the not parallel step 8. And so what we had here was the sort of full FMM that skips the empty boxes. And so the difference between step 7 and step 8 was that we introduced these maps that map between the full Morton index and the skipped index. And so cells maps from the skipped index to the full index, and cells 2 maps the full index to the skipped index. So you can go back and forth by using these two arrays. You can turn one index into the other. So you can go back and forth between the full and skipped, then the non-empty index. So now, the last thing I think we did was to change the level offset so that it uses the non-empty one, not the full Morton index. And so the memory consumption should be like optimal right now. It only stores the boxes that are not empty. And so, and we checked that this was working. Let me check again just to make sure that it's still working. So if I do step 8 and run it, the two numbers should match. So it's showing, if you remember, it was like 209 something something. And it's matching on both sides. One is from the direct summation, and the other one is from the approximation. And so the last thing, so what we want to do today is to change this code so that each of these kernels, P2M, M2M, M2L, these things, this part here, turns into the high order calculation that comes from the Taylor expansion. So to do that, first, I want to make this part into like a function call so that it calls a function called M2P, and then it returns this thing here. Because once it becomes a function call, I can just change the function inside of the function, and then it will automatically, change here without, I don't have to touch the rest of the code. So I want to wrap this operation here, although it's just one line. I want to put this thing inside a function. And the same for all the other ones. I want to put all of these things inside of a function so that I can calculate the other kernels. But before we do that, we need to know, for example, right now we're only calculating the first term. So we don't need, for example, the coordinates of the box and the bodies to calculate the multiple expansions. But once we go to high order, we need the information of the coordinates of the center of the boxes and the bodies to do the P2M and L2P. So first, maybe we will try to calculate, put these into a function call. But then the next thing we need to do is to actually make sure we're able to calculate the coordinates of these things. So once those two things are done, I have the kernels ready in a different file, so I'll just import those high order kernels, and then we should be good to go. So yeah, also this P2P and check answer part, we can change into like a function call so that it just takes in some number, and then we can just change the equation however we want it to. So, okay, now let's do that one by one, starting from P2M. So what we want to do is to change this into some function that calculates, this M term here. And we need to have a AND here for it to return the value. Otherwise, it can't return the value. So, and then we have QJ here. But in the future, we want to have the coordinates of the boxes also being passed. But for now, we will just pass this P2M. So the input is Q, and the output is M. It doesn't make any sense right now because it's just one line anyway. But when we make this complicated, I think it will make more sense to have this as a function. Okay, so now we define the function to be this line here. So if you go maybe outside of the main function, here, and define something called P2M that takes in this. So since we're inputting already with the index, we just need to, I think we just need to write like this, because the index is already being specified before we pass it. So we're just passing one number, not the array. So we don't need to have the index here. And this is useful because when we introduce the more complicated kernels, we don't have to have all that index complication here. We can just put the equation in a very simple form, and it would be more intuitive what we are calculating here. Okay, so let's check. Oh, I should have saved 8 to step 9 because I want to preserve step 8. Okay. So because I have this version controlled, I can actually change back to the original state. So see, step 8 is now back to its original form. Okay. Well, for those of you who didn't have it saved, you can just download the old one again. Okay, step 9, I'm going to do like a, call it kernel function, because we're defining all the things that were in mind now as a function. Okay, P to M looks like this. M plus equals Q. Very simple. It's actually closer to the actual equation that I showed on the slide, but this is only, I need to have the star here. Yep, still working. Okay, so because I'm passing in this as a pointer, I need to dereference it here like M. Okay. If this was C++, I can just put and here and use just M, but because this is C, I need to write it like this. Okay, so we will change this gradually, but for now, this looks okay. So now we did P to M. Okay. Now, the next thing is the M to M kernel. So we'll do the same thing, right? So we just take in this whole thing as the output argument, and then we take this whole thing as the input. And remember, the input, it doesn't need to have the and mark because we don't have to write to it, so it doesn't need to be a pointer. Okay, now we move this whole thing to the function definition that's next to P to M. We will do like a M to M, and well, actually we don't. So we need to make sure that this is named, they're both M, so we can't just name them both M. Maybe I'll call this MI and this one MJ. Okay, so star MI plus equals MJ, like this. Okay, this is the new M to M. And it's just one line of code for now because the kernel is very simple right now. But let's see, oh, sorry, I'll keep this window open and then, like I've been doing before, I will operate on this side so that you can still see the code while I'm compiling on this side. Okay, still matching, so we're doing good here. Okay, now I move to M to L. So the good thing about rewriting like this is that all the complex code is done outside, and you're only doing the mathematical operations inside. And so it's very easy to change the kernels to a more complex form. Okay, now I'm going to copy this thing here. Oh. This thing here to, and this needs to have an and again. I'm just copying what was written down here and adding it as an input parameter to the function M2L. So what I'm doing is very straightforward and putting it here. You may not be able to see the whole screen, but I'm just copying over what was L and M and putting it inside M2L. Okay, now I go up and calculate void M2L and now double. Again, I can just say this is MI and this is MJ. But this time I'm not doing plus equals. I need, oh sorry, this should be L and M. And this time I am adding M divided by, oh, so I should pass R, right? R needs to be passed. double R. So this is an example where it's actually calculating the distance R. We need to do this for the other kernels too. Well, not necessarily R, but we need to calculate this distance dx and dy eventually for the other kernels, because the higher order terms for P2M, M2M, L2L, and L2P also use this dx and dy. So yeah, perhaps a better way would be to input into the function something that determines dx and dy inside the kernel. But it's okay. For now, we'll just input R here. Make the changes gradually. I don't want to break the code. So yeah, still okay. So then L to L, one change at a time. So for L to L, I will add this part here. And put an and mark. And then this part here, I add here, and I define L to L up here. Double, okay, I'm now going to use Li and Lj because they're both L. So Li equals, or plus equals, okay, this should give me the correct answer. Step 9.c. Yes, okay. So now we finished up to L to L. I'm doing the same thing for all of them, just taking this one line that I'm calculating and changing it to a function call with the appropriate kernel name. And for this case, it would be, output would be uj, and the input should be this L thing here. So I'll just copy this thing to the box here. And this is also a plus equal operation, so I'm going to define up before the main void L2P double star U and double L, and U star U should be L. Okay, let's see if this is giving still the correct answer. Yes. Okay, now we are almost done. I think I'm also going to change the P2P. Okay, so for this case also we need to input R, and so P2P, I'm writing to U, I, and inputting QJ and R, like this. And then I can just copy over this one line to function definition void P2P double U Q R. And so this R not equals to 0 still works because I'm passing R as an argument. And I don't need the index for u and q. So this becomes star u plus equals q divided by r. Let's see if this one still works. Yes. And now the good thing is I can use the exact same thing for that check answer. And when I change the contents of P2P, at some point, if I want to, I'm assuring that both parts will be changed in the same way because I'm turning it into a function. So it's good. So all I need to do is change this check answer part to like this, and then, okay, so now it's running, like giving the same answer. So step 9, I think we're okay. Just we will leave this as step 9. And I will upload this code now that it's finished. Step 9, I upload to, okay, Google. Yes. Okay, I think it's uploaded now. So if you didn't follow, you can just download step 9. I just changed each of the operations to a function that has the name of the kernel. So I define P2M, M2M, M2L, L2L, L2P, and P2P as a function. And now I will copy this to step 10 and step 9 to step 10. And then what I will do is I will import, or no, first I need to pass the coordinates for each of the kernels. So before, I didn't need, for example, the x and y calculation for P2M because it was just summing q. But if you look back at what we need, so I'm going to open the equation slide just to show you why I needed to change. Where is the, yes, here, or maybe this one is better. Okay, so we want to change P2M into this thing here, and M2M into this thing here, M2L to this thing, L2L, L2P. And what we need here is, before we didn't have x vector, but now we need the x j prime j vector, which is the distance vector between the center of the box and each particle. And also here, we need to have the distance vector. And here, also, we need to have the distance vector. So at each location, we need to have the dx and dy, which is the distance between the 2 points that we're calculating. So I will now change the function so that they take in as input the dx and dy. So that should be enough for me to calculate all these kernels. Okay, so it's just one change. I'm going to change so that P2M, M2M, M2L, L2L, and L2P, they don't calculate the high order terms yet. I'm just going to change the input so that they can take in as an argument the dx and dy, because that's a necessary step before we move on. Okay, so how do I calculate the center of each cell? So I need to first calculate the center of each cell. So I can do this from the Morton index, right? Because so it's already doing it here. This is the answer, because here I'm doing it. I'm using get ix to get the two-dimensional index. So remember, this cells thing will map my non-empty index to the full Morton index. So this cells at level L, IC, is going to return to me the full Morton index. And then if I input this to get ix, it's going to give me like either like two numbers, 1 and 3, which represent where my box is. From those numbers, if I have the, let's see, so that number divided by nx is not actually, so so there's a little bit more math involved than that, because think of what these coordinates are. So this is a good example. Look at this picture. So we define all the points by drand 48 to be between 0 and 1. So this whole domain, we know that it starts from 0 and goes to 1. And we know that all these boxes are here. So it's very easy to calculate the center of each box. What we do is we know that this is 0 and this is 1. So if this is divided into 4, then first what we need to do is to divide the 0 from 0 to 1 by 4. So this is 1/4. This is also 1/4. The size is also 1/4 and 1/4. And then the center is at like halfway between those numbers. So if this whole box was 1/4, then this point is at 1/8 and 1/8. This one is at 3/8. This one is at 5/8. And this one is at 7/8. So we will use that kind of math to calculate. So I think the simplest way to express that would be to do, first calculate how many boxes it's divided into in each direction. That we are using a variable nx to define that. So we first divide the number that we get by nx. And the number that we get here should be, so if we get 0, 1, 2, 3, we need a way to translate 0, 1, 2, 3 to 1/8, 3/8, 5/8, and 7/8. So it's like multiplying, well, first we need to subtract, like 0.5, or add 0.5 to that number, and then divide by nx. I think that will get, so, well, I can try, see if that's correct. So first I'll do this. So I'm going to attempt to get the coordinates for, this is level, and I. Okay, so ix will be a number between 0 and printf. I'll print the numbers so we can check as we go. It's always good to confirm, even if you think you know the answer. So I'm going to print I, the index of the cell, and then ix, two numbers. Okay, I'm going to print this thing here. Okay. Okay, it's printing numbers between 0 and 8. That's because it's level 3. So this example, step 10, is calculating this level here is at 3. So the number is between 0 and 7. And so once we get this two-dimensional number, to determine the center coordinate, we calculate from Ix let's have, what's the Ix times, I don't know, plus 0.5 divided by nx. nx is this thing here. We know that nx is the number of boxes in each direction. So in this case it's 8. This will give me back 2 to the level, and level is 3, so it will give me back 8. I will divide this by 8, and this should be the coordinate of the box. So if I say that x is the coordinate of the box, x and y, so these are the two coordinates of the boxes. So I will try to print that along with the Ix and Ix0 and Ix1. So let's see if I am calculating this correctly. Before we move on, it's good to check that this is being calculated correctly. Step 10. Okay, so if you look at the numbers, so when it's 0 and 1, it's like here, and when it has a big number, 6, so it's still within, yeah, I think these numbers look correct. At 1, it should be, so when it's 0, it's like halfway, and you're also dividing that by 1/8. So the size of the box is 1/8, but the point is at half of that. So that's why there's this 0.5. So by adding this here, I think I'm getting the center coordinate. You see, because the center is like, it's like half in the center of the box. So if the length of the box is 1 over nx, then sort of adding 1.5 before dividing will give you the center of the box, if this number goes from 0 to 7. Okay, so now we have the center of the box. And now actually I don't need to store this in like a separate value, because I'm immediately going to subtract here x, wait. So I'm going to put this inside the loop for x, for the bodies, and then I'm already going to subtract immediately from because what I want to know is the distance between the center and the box. So and the particle. So once I calculate this thing, I'm immediately going to subtract from xj and yj. J is the index of the particle. Okay, so I'm getting the dx and dy, sort of in the same way that I'm getting it for the other kernel. So dx and dy. And from dx and dy, actually, I can calculate r. So I don't need to pass r. I just need to pass here dx and dy. Or maybe I should pass it before q. Or no, I'll just pass it after q, because it's easier to change for the other kernels too. So, okay, so I'm going to do this for all the other kernels too, except M2L is already calculating this, so I'm just going to pass that. But I'm going to calculate dx and dy for the other boxes, and then keep passing them into the new kernel that I wrote for each case. So let's go to the P to M kernel, although it won't be used yet, because we're still doing only the first term. But I'm going to just write here double dy, and I know I'm going to do that for the same thing, so I'm just going to go ahead while I'm up here and just change everything so that it has dx dy, and then here, instead of inputting r, I'm going to input double dx and double dy, and then from this input, I'm going to, inside the function, calculate r. I should be doing this for all the other kernels too, but dy. Okay, so r can be calculated from dx and dy like this. So I'm just going to keep adding double dx and double dy to all the kernels that I've defined. Although they won't be used for most of the kernels. And again, for P2P, I can again calculate r from dx and dy like this. Okay, now I changed everything in the definition, function definition, but I haven't changed all of them in the function call here. So now I need to make sure I'm calling dx and dy. So now I need to do the same thing for m to m, but maybe there's a better way to do it for these parent-child distances, because no, I'll just do it in a simple way. Yeah, I already have nx, and I need to calculate the get ix for level L. For cell I, like this. And then the parent cell is what? Ix. So Ix divided by 2 is the number of the parent cell, but it should be divided by a separate nx, right? Okay, so this plus 0.5 divided by nx is the, so this is the position of the current cell, and for the parent cell, it's Ix divided by 2 plus 0.5 divided by, not by nx, but nx divided by 2, because it's like parent has half the number of subdivisions. Okay, I think I can simplify this equation somehow, right? Because if I know this, and if I know that I'm dividing here by half the nx, is that equal to multiplying this by 2? And this by 2, which becomes plus 1. Well, okay, I won't change this until I have this working. Once I have everything working, it's easy to confirm by just running the code. So now I'm just going to do what I'm sure will work. Okay, so the function is the following. So for the parent, you need to do plus 0.5 still, but you divide by half the nx, like this. And nx is always a even number, so dividing by 2 is always okay. It will give you the correct number of subdivisions at the parent level. So the logic here is I am subtracting the current level from the parent, the current coordinate. I think I need to subtract the other way. I need the destination to be first. So let me change this part. The parent coordinate needs to be first. It needs to be the part where you subtract from. So here, I'm just changing the order of the subtraction. I'm moving the parent forward. So this part needs to be in the front. The parent needs to be in the front. I'm subtracting the child coordinate from the parent because the destination needs to be in the front. Okay, so now dx and dy I have. Okay, so I'm just inputting the dx and dy that I calculated here into the function like this. Okay, maybe I can even put this whole thing inside this if statement because it will save time to calculate. Although it's not a very critical part of the FMM code. This part will take almost no time anyway. But okay, so dx and dy I've calculated for p to m and m to m so far. The good thing is L to L and L to P are symmetrical from P to M and M to M. So I can just copy and paste these things for P to M and L to P. So here, but again, the direction of the subtraction needs to change because for the L to P, I need to be subtracting from xj and yj. Because that's the definition of, and then input that to dx and dy like this. Okay, so this is for L to P. I just copied from P to M. Again, also from M to M, I can just reverse the direction. So this part that I was subtracting, I will now put in the front and subtract from. And this part here, I put in the front and subtract from. So here now, this is the dx and dy that needs to be done for the L to L. I'm subtracting the parent coordinate from the child's coordinate. And for M to L, I already am calculating dx and dy. So for M to L, I'm just going to change this r to dx and dy. And I don't need to calculate r here anymore. Okay, and then P to P, I am also calculating dx and dy here, and I don't need to calculate r anymore. So also same here, dx and dy for the check answer I am calculating already, so I don't calculate here. Okay, so now everything should be working. Step 10, I think I typed something wrong somewhere. 193. I forgot to put the L to L. I forgot to put these braces. Okay. Step 10.c. Still giving the correct answer. So I have successfully added these distance vectors, dx and dy, to all the functions. So we're almost there now. Now the final thing is to just change the kernels that use these things to calculate the high order expansions. And I've prepared them already. Well, I've written FMM code somewhere else, so I'll just take it from there. But the basic structure you follow, right? The only thing that I'm going to change now, going to step 11, is to just change what's inside L2L or L2P or all these functions to something different. Everything else will remain the same. Except I think there's one more step, like an intermediate step that I can take, is L right now is just one number per cell, right? It's just, I'm indexing it by just the cell index, and I'm assuming inside all the functions, if you look at my kernels right now, I am saying, so for all of these ones, I'm treating these m's and l's as scalar values. Okay, there's only one number. But I want these to be like an array of all the expansion coefficients. So, for example, if I'm doing like p equals 6, this needs to be like an array of 6, for example. Okay, and also, there's another small detail about the kernels that I'm going to introduce. They're going to be complex numbers. Okay, so maybe I should explain this to you before I introduce the kernels, because the kernels I wrote here were not complex numbers. But so when you do this kind of Taylor expansion in 2D, like 2D Taylor expansion, it turns into many terms if you're using a real number for these values. But consider if this x was a complex number z, which is equal to x plus iy, which is like, so if you use a complex number, you can express the two coordinates with just one scalar complex value. And then this Taylor expansion turns into actually a 1D Taylor expansion, and everything becomes very simple. So although complex arithmetic is introduced, it actually simplifies these vector powers and vector factorials and vector summation indices to a scalar. So I'm going to introduce a complex number expansion. Well, it's the same thing. I'm just going to introduce these equations, except for x, I'm going to use z, a complex number that's a scalar, and not this vector x, which is xy. It's not a set of two numbers anymore. So the math becomes simpler, and also the reason is because I already have a code that calculates that complex one. So before I go to this step of introducing the complex numbers and the proper high-order kernels, I'm going to introduce one last intermediate step. So step 11 will introduce, let me introduce, so first I will copy step 10. I'm done with step 10, so let me upload step 10 like I uploaded step 9, so that you can start from there if you didn't follow. So step 10, yes. We'll go to my Google Drive, and it's updating. Okay, now step 10.c is uploaded, so everyone can download and just run. Now I'm going to move to step 11. Okay, so I will now, step 11 is complex coefficients. Okay, so what do I change? I change M and L, these two things. So it says double here, but I'm going to turn these into complex numbers. And to use complex numbers, wait, I have a complex number in C++. So complex numbers in C is different, right? I need to use, is it the same? Double complex. Okay. Include, I'm going to include the header file complex.h because I'm going to use complex numbers. Okay. And then all of these doubles will turn into like a double complex numbers. Oh wait, I'm not entirely sure how this, because I don't usually use C, so works like this, right? Double complex, and that becomes a type. So yeah, let me change M to double complex, just a test and see if it breaks anything. Okay. Okay, so I have to change only a few things, I think. I'm not sure if I can do like double complex, assign 0 to these numbers, but we'll see soon enough. I just get warnings. I'm getting the correct answer still, but okay, so I think this is still okay as a code. So I'm going to now change all the, both the M and L to double complex because it seems to be working. Okay, now let's see if step 11.c is still, good. The warnings went away. Okay, now it's still giving the correct answer. So now I've changed M and L, those two arrays that were doubles, they are now complex numbers. Okay, so how do I printf a complex number? I just want to make sure I can. Oh, so you need to separate the real and imaginary part? Yeah. Okay. So now the next thing I want to introduce is to make these arrays, change the size. They were scalars, but now I want to make them like size p times the number of boxes. So I'm going to change all of the m and l so that they get indexed by p. I'm going to define p here. So p, let's use 3 or something. Okay. P is the order of expansion. We will introduce the order of expansion p now. And so I'm not changing anything inside the equations yet. I'm just changing the data structure to complex and then to an array with p numbers in them. Okay, so M and L are now two-dimensional arrays of p by number of cells in the whole tree. Okay, and when I do this, I am passing, by doing this, I should be when I index like this, I don't need the AND, right? So this will be a pointer to the first. Yeah, I think I just need to get rid of all these AND. So all the parts that I had AND for the, or not the U, because I'm not changing the data structure. Okay, so the interface is now changed. I am passing a pointer to the first element. So this thing here that says M star is now I'm actually passing in like the first index of the array. So there should be, this should be like, if I change M0, because essentially M0 is the first term, and this is what we are calculating here. So all of these equations we're just calculating, and I need to make all the M's and L's stars now, even the ones that I'm just reading. They are all arrays, so I'm passing the pointer, and I'm inside. I'm just referencing the first zero, or the zero element number 0. Like in all these things, I change them to star, and then I index by 0. Change the input to star, like also this one to star, to a pointer, and then I'm going to index all of them with 0. I think this should be okay. So I've changed all the interfaces to make it, I'm initializing, I didn't update the initialization part. That's why it's complaining. So it's saying you're treating them as, yeah, so why don't I just initialize them like I should with like a 2D thing. So I need to initialize the whole, initialize the whole 2D array up from 0 to like p minus 1. So because it's size p times, the number of cells. So okay, now I've changed that, so it shouldn't complain. Oh, okay. It seemed to be doing something bad. Okay. I think I made some yeah, these should all be pointers, right? So why is it not working? So the compiler is not complaining, so there's nothing syntactically wrong. Maybe this needs to be P? I'm not sure. Let me print and see if it's stopping here. Because I just changed it to an array. That's the only thing I changed here. Okay, so yeah, it's likely that it's failing here, I think. So let me check if this is true. So it's saying there is no M0, I think. Yeah, so it printed the before but not the after, so it's giving the segmentation fault here. So oh, maybe I have it in the wrong order. So maybe P should be like because the name should be Oh, but either way, I'm only accessing the number 0 element, so it shouldn't complain. But let's see if this is... Ah, okay, yeah, I think that was the... So now it's working. What I did was I just flipped the order of the two-dimensional array for M and L to have, like, the first index is the cell index, and then it's like a, yeah, so it's an array of like MP arrays. So I'm indexing the, yeah, MP array, the index of the MP array. Okay, and the P is the ladder, yeah, so that like this. Ladder index. Okay, so now I think we are ready to just plug in the kernels I have. So I'm going to save step 11, the working thing, as step 11, and then the final step 12, I'll just swap the inside of the P2M, M2L, M2L, M2M, M2L, and L2L, L2P, P2P, all the kernels, so that it will work. So step, and I'm going to upload step 11 now to the Google Drive. Yeah. Okay. I think unless something goes terribly wrong, I think we have enough time to finish the full FMM because it's just changing the kernels. Okay, step 11 is uploaded. Okay, final step, number 12. High order kernels. Okay. So now I have these kernels P2M and so on. So I have 2D kernels inside another code. Okay, P2M. Except it's written in C++ with structures, so I need to somehow extract just the calculation part here. dx2 is the dx and dy vector that I'm passing, so I need to first turn this into a complex number. Yeah, right. So double complex z is dx dy. Can I do this? Let me first check if this is okay to do. Ah, no, this is not okay to do. Okay. Yeah, because this is C++ type of initialization. Needs to be like I, big I is like a predefined variable or something. Like this. Maybe this is how. Okay. So then, now that I know how to use this, I'm just going to copy over all the contents from this. I'm defining also another thing that is for calculating the powers. So this thing, double complex, pow z is like the power. It starts from 1 and then it's for calculating the power. Because there's a power in the Taylor expansion. So I just using this to accumulate the powers. Okay. And now I just need to loop from okay, so I'll loop from n to from n1. So 0 I'm already calculating, but the high order terms I need to calculate in loop. Like this. And P is only defined outside, and I'm not passing P, so this, I need to make sure to define P as a global variable or something. Okay, so this is a new P to M kernel. And changing just this part won't harm the other parts of the code, because it just, all the other parts of the code only reference M0, so it doesn't matter what I put inside the high order terms for M. It's just not going to use them. So the answer should still be the same. I'll check if this code is working. Yeah. So I'm just going to define P like outside, like here, because okay. Okay, so still I'm getting the correct results. And now I have a proper high order P to M kernel. Well, we don't know if it's giving the correct answer yet because we haven't confirmed, but I think it's okay. Now let's move on to M to L kernel. There's one thing that's different. It's subtracting the other way in this kernel. So I should make sure. So it's in my other kernel, for some reason, it's subtracting this other way. So I should match the definition here, because okay, so P2M, the dx and dy were defined like, well, you can pass minus dx and minus dy. Maybe that was faster, but okay, so now everything is matching. The definition is matching, and I am going to move to the M2L, M2M kernel, which is this part here. Okay, so Same thing, I'm defining the z again. And let me make sure that the direction again is the same. So Cj. Oh, again, I think the direction of the sign of dx dy is opposite for my calculations here. So I'm going to just pass in minus dx and minus dy. Okay, so m to m is, I'm going to use the same definitions of these z and power of z. And here we just need to loop over, what is this KML thing? It should be okay to just use n. I don't understand why I'm using this strange number, or strange variable name. Okay, so again, power of z is z divided by n, and mk plus equals mk minus n times power of z. I think that's what it says here. Yeah. Okay, so that it's very simple change. It's not a very complicated code. I just added, the factorial. Actually, the pow z is like calculating the power of z, and also divided by the factorial of n, because n is increasing from 1 to k, and then it's being multiplied to the original number again and again. So it's taking the power of z and factorial of n at the same time and putting it in power of z, which was the definition, if you remember. 1 over factorial n times the power of the vector x, xj prime j double prime. So now we have all these values. Let me just make sure that n could be start from 1, so this will always be smaller than p minus 1, right? pk could be, no, where is the loop for k? I'm missing the loop for k. Yeah, there's another loop outside here for k. I'm sort of missing an outer loop for k. Yeah. Unless I calculate this outer loop for k, I'm only calculating the first term of the parent expansion. So I need to change this thing here, not from 0 to k. Okay, so now when k is 0, it just calculates the original thing. And yeah, so this should be okay. So now it's calculating mj. Okay, since I'm using the variables mi and mj, I need to, so this is mik plus equals mjk, and then looping n from 1 to k, calculating the factorial and the power of z, and then multiplying that to mj, k minus n. Okay, good. So now I will check if this is working. Oh, and we could take a short break, like a 10-minute break, if this compiles, because we have another 50 minutes to do M2L, L2L, and L2P, and P2P. Okay, good. It's working. So let's take a short break. But I think we have enough time to finish everything. So I've just added the P2M, M2M kernel. If you remember, this is, if you think of this Z as like the scalar, vector, distance vector, and remember the original definition that we covered in the first lecture, just so that everything makes sense to you, even though I introduced the complex numbers. So basically it's still doing the same thing. So we have n factorial. So this is the P2M kernel shown here. N factorial times the x to the nth power. This is being calculated here because I'm taking the power of z, which is like, you can think of it as the x vector, and if I multiply equal n times, it's going to turn into the power of z to the n. And this part, n is increasing from 1, 2, and 3, and then it's being divided by those numbers with the multiply equal. So it's like the factorial of n on the denominator side. So once you multiply that to q, you see that it's calculating exactly this. And it's just looping over all the points inside the box. So every time it does a plus equal, it's just adding to this, like this summation mark here is being done on the outside loop. So inside loop, it's just generating all the terms for n. And it's storing each n, for different n, into a different part of the array, so mn. And so if you look at the m2m, you see that it's calculating exactly this equation here as well, although the difference is that x vector here is expressed as a complex number z, but that doesn't change the form of the equation. So n minus k factorial is being calculated this should be n minus k. Instead of the n, because it looks like I'm calculating the n factorial there. Or maybe I swapped variables. Yeah, okay. I think I swapped, so I changed the definition. So the reason why n is going only up to k is, well, it's still strange because m to the k. So this one is turning into k minus n, and this one is turned into n. The k is okay, but it's like a redefinition. So if I change k to n, it would look like this. And if I change n minus k to k, it still looks a bit different from this one. So n goes from basically 0 to k. 0 to k goes from 0 to n. I wonder what happened. But okay, so once I figure out what happened with the n minus k power here, you can still see that it's calculating the same kind of factorial here and the power here. So this pao z represents this part here, and mk is written as k minus n, because I think the definition is slightly different for the k and n. But anyway, this will calculate all the necessary terms for this equation. So all of them will be in this new array mi now. And so I'm calculating this thing. Okay, so the next task is to calculate this one, and this one. So because I'm just copying from a code that's working, I'm sure the end code will work. And now that we've successfully added all the complex stuff and it's running with the complex, it's just a matter of adding 1, 2, 3, 4 more equations in the next 50 minutes. Okay, let's take a break for 10 minutes and we will resume. Well, you can try to download. I'll upload this code as it is now, and you can try to check if it's working. Okay. Step 12 is uploaded.